Hi, this is Alfozia Nihar from At Home Tuition. Welcome to our session today. The topic that we are going to discuss in our today's video is the second part of our previous video, definite integrals of piecewise defined function. Here, first let us start with how to find whether a piecewise function is continuous or not continuous. When you're given a graph, you can easily tell that whether the graph is continuous or discontinuous just by looking at the graph. You can check whether there is any jump or any broken pieces, any incomplete point. But when you're given the function directly, how will you find whether it is continuous or not continuous? To tell if a piecewise graph is continuous or not continuous, you can just look at the boundary points and see if the y point is same at each of them. If the y's were different, there would be a jump in the graph. So let's try this with few examples. Here is an example. Please look at this question. Here is a piecewise defined function. In the first part, we have negative 2x plus 8 if x is less than or equal to 4. If x is greater than 4, the function, the rule is going to be different, 1 over 2x minus 2. So let's check at x is equal to 4 in both parts of the function. Since 4 is the boundary point. Boundary point means the common point, okay, the point which lies in both. Actually, this is lying on the first one and this is the endpoint for the next function too. So let's check for x is equal to 4. I'm going to replace all x by 4. If we replace x by 4, we get 0 on the left side and on the right side also 0. Yes, both the pieces. This one is also 0 and this one is also 0. So if you get the same value, it means that the piecewise function is continuous. Does this make sense to you? Now let me take one more example and show you a non-continuous piecewise defined function. Here is the example. Please go over this function. So let's check in the first two parts of the function. Note that in second part, y is always 2. And for this one, 1 plus 4 will give you 5 and this is 2 equal to 2 always. 5 cannot be equal to 2. Am I right? So we can stop here and note that this piecewise function is not continuous. If the y's were equal, we would have to go on to check the next boundary point, x is equal to 4. First, the boundary point for these two is 1 and for these two is 4. You can check for 1 and if it works out, you can then move on to the second set. Hope you're clear with this one. This is a non-continuous example. Next one is graphing piecewise functions. You will probably be asked to graph piecewise functions. Sometimes the graph will contain functions that are not continuous or discontinuous, meaning that you have to pick up your pencil in the middle of the graph when you're drawing it. It is just like a jump. Continuous functions means that you never have to pick up your pencil if you are drawing them from left to right. And please remember that the graphs are true functions only if they pass the vertical line test. Hope you are all familiar with this. If you are going to draw a vertical line on the graph, it should touch the graph only once. In case if it touches the graph more than once, then you can say that the graphs are not true functions. So let's draw the piecewise functions and determine if they are continuous or not continuous. Please note that how we draw each function as if it were the only one, and then erase the parts that are not needed. So we will also get the domain and range. Hope you are familiar with this topic too. For more information on domain and range, you can refer our previous video. Here is the first example. Here is a piecewise defined function. Now let's graph it and then check whether it is continuous or not continuous. For this one, x is less than or equal to 4. So let's find the domain and range for this. Domain for this one is going to be negative infinity to infinity because it is considering all the numbers less than or equal to 4 and all the numbers greater than 4. So the numbers will start from infinity and end at negative infinity in case you are imagining the numbers on a number line. So domain is going to be all the real numbers. And what would be the range? Range is from 0 to infinity. Let's do the graph. If I draw a vertical line here, it will touch the graph at the only one point. Am I right? And if you look at the graph, you can say that it is continuous. So for finding the graph or graphing the piecewise function, you should know the domain and range. You can just draw the graph and do a vertical line test. In case if it does not not passes the vertical line test, you can say that it is not a function. Okay, let me take one more example, the same example which I took previously. Here is the next example. It's also a piecewise different function, x plus 4, 2 and x minus 5. So there are different boundary points here. First let me graph it. Here is the graph. By looking at the graph itself, you can say that it is broken into pieces and some points are not included. So obviously this is not a continuous. Even if you look at the domain and range, just look at the domain and range, it includes all the real numbers, domain and range, that also includes all the real numbers. And if you draw vertical line, for example, here I have drawn a broken line, no, please look at that. It touches more than at one point, am I right? So it does not pass the vertical line test. So this function is not continuous. In your higher level classes, you will be allowed to use graphing calculator. If that is the case, your job is going to be very easy. Everything is going to be easy using a graphing calculator. Next important thing about this topic is finding equations from piecewise function graphs or piecewise defined functions. Let me take graph. So you may be asked to write a piecewise function by giving you a graph. Now that we know that what a piecewise function are all about, to review how to obtain equations, let us take few examples. Here are the graphs. Here is a graph. Please have a glance over this. So from this graph, we see that our boundary lines are at x is equal to -2 and x is equal to 1. So we know that our function will look like something like this. Notice open and closed endpoints. So this is the limit. And now we can pick 2 points, -2, 0 and -3, 2 on the leftmost line to get the equation -2x minus 4. Am I right? And in the middle function, we can see that the middle function is x square minus 2 and the rightmost function is just the horizontal line at y equal to 2. Here this point, the point on the y-axis is 2. So the piecewise function is going to be minus 2x minus 4 for x is less than -2, and for this interval -2 to 1, it's going to be x square minus 2, and for x is greater than or equal to 1, it is just a straight line. So obviously this is going to be a constant number 2. So this is how we derive the equations from piecewise defined function. So you have to concentrate on the points where the graph is focusing on. Here it is focusing on 2 and 1, and here it is -2. So based upon that, first you can derive the boundary points and then you can find the corresponding equations. Hope you are clear with this concept. Let us discuss one more example. Here is the next example. Please have a glance over this graph and notice that at which point the graph is moving upwards and it follows a straight line, and you have to notice all the changes, all the movement, the directions the graph is moving, the curve is moving. By looking at this graph, we see that our boundary line is at x is equal to 5. Am I right? If your graph is up to the scale, you can easily do that. Okay, the boundary line is at x is equal to 5 and the line meets at 5 and 4. 5 on the x-axis and 4 on the y-axis. It does not matter where we put the less than or equal to or greater than or equal to sign. We can't just put it in both the places, or it would not be a function, because a number should be included in only one piece, not in the other piece. That's the reason these symbols are different. Less than or equal to and greater than, or less than or greater than or equal to. So for this graph, we can have x is less than 5 for one piece and greater than or equal to 5 for another piece. Again, now we have to look at each line separately to determine their equations. So we can either take 2 points from each line to get these, or derive from slopes and y-intercepts. That is also one interesting type of deriving the equations. You can derive from the slopes and also the y-intercepts. So here this piece for x less than 5, I can say that 6 over 5. The slope is 6 over 5, x minus 2. And for the greater than or equal to 5, 2 over 5 x plus 2. You may also get word problems, and many types of different problems can come under this topic. These questions are very straightforward. A graph will be given and you'll be asked to find the equations. But when it comes to exercise problems, you may also get word problems. We can discuss few of them in our next video. Also, we can discuss absolute value piecewise different function and how to derive the equations and all in our next video. In case if you get any query regarding this video, please let me know. See you in the next video. Thanks.